Capillary action. Section on physical properties of fluids. In the previous two lessons, we learned about surface tension. Now in this lesson, we will talk about one of the products of surface tension, capillary action. First of all, we saw this picture right here, and we said that the liquid in a solid tube like this can either wet the surface or not wet the surface. We said that this curved line on top of this liquid is called a meniscus. It takes a concave shape or a convex shape based on the surface tension of the given fluid. The meniscus is very important when reading U-tube manometers and measuring fluids inside of instruments and lab glassware, because we have to define what exactly is the line and what is the volume inside the glassware. So is it the top part, is the middle part, or the bottom part of a meniscus? The word meniscus comes from the Greek word meniscus, which means crescent, as in a crescent shape, a curve. On the other hand, the name capillary comes from the Latin word capilla, which means hair. Capillary action is when we have the rising or falling down of a liquid inside of a confined solid object, such as a glass tube that we can see here. Now here we have different diameters of glass tubes, and we have a fluid. Mind you, this is the same fluid in every compartment of this glass object or glass instrumental tube, which gives us the idea what capillary action is. So we have the widest test tube, and then we have the thinnest one, which has the smallest diameter. And we can see how the fluid arises inside of it. We will see why and how in a bit. In the situation with capillary action, we have three mediums in contact. We have a liquid, we have a gas, in this case air, and we have a solid object. And this solid object has to have one dimension that is much smaller than the other dimension. So in this case, a small diameter compared to the long length. What is behind this falling down or rising up of the fluid? Now, in this case, we have a liquid that rises to the top. Well, the forces of adhesion and cohesion are responsible for this. Simply put, adhesion is the attraction of molecules of different chemical substances. So this means those are intramolecular forces. And cohesion is the attraction of molecules or atoms of the same chemical substance, which means that these forces are intermolecular. This little illustration tells us everything we need to know about adhesion and cohesion. So we have these two molecules that are the same, and between them we have cohesion, and they are grabbing onto another object or whatever, which is not made from them, so to say, and between them and this other object we have adhesion. These forces are both present when we have such a medium. So we have air, we have a solid object, in this case the walls of a glass tube, and we have a liquid. We have water, and we have a liquid metal, mercury. Wetting of the solid object happens when the forces of adhesion are larger than the forces of cohesion. This happens in the air-water glass scenario. This meniscus is going to be concave in this scenario. The forces of adhesion are perpendicular to the wall. They are directed to the wall of the solid glass object. And the forces of cohesion, being the forces that are intermolecular, so the molecules have to be attracted to their own molecules, are directed to the mass of the fluid, of the liquid in this case, right? These are the intramolecular forces, the forces that happen between water and a solid object, and these are intermolecular forces that happen between water and water, so the same molecules. So when we plot these two forces, and when we plot a resultant force of these two forces, what we get is a resultant force that looks something like this. The resultant force is also perpendicular to the free surface, okay? So this is the free surface of the liquid, and this is the curve, right? If I continue this curve, it would look something like this, right? And this is a tangent line on this free surface. And the resultant force is perpendicular to this tangent line. This is when we have forces of adhesion that are bigger than forces of cohesion, and this is when we have wetting of the solid object. On the other hand, non-wetting of the solid object happens when the forces of cohesion are larger than the forces of adhesion. Same thing with forces of adhesion. The direction of the forces is the same. The only difference in this case is the magnitude of these two forces. Now here we have the forces of adhesion being in the direction of the solid object, the wall of this glass tube or whatever. We have the forces of cohesion directed in the mass of the fluid, and when we plot the resultant force of these two forces, what we get is a force that looks something like this. So this would be the resultant force in mercury, for example, because intermolecular forces in mercury are much larger than in water. What we have is cohesion being much stronger than adhesion. We have the non-wetting scenario. Okay, remember that. Again, the similar situation like we had in the adhesion situation. Only this time the tangent line looks a little bit different. So the tangent line follows this curve, right? Sorry, one second. So the tangent line of this curve is something like this. The curve of this free surface, the liquid free surface, looks something like this, and this is the tangent line, and the resultant force R is perpendicular to this tangent line. It follows the tangent line of the curve of the free surface of the liquid. So this is the situation when we have non-wetting, when the forces of cohesion are larger than the forces of adhesion. So the shape of the meniscus tells us if it's a situation of higher adhesion forces or higher cohesion forces. When we have a concave meniscus, the forces of adhesion are larger than the forces of cohesion. When we have a convex meniscus, the forces of cohesion are much larger than the forces of adhesion. In the next lesson, we will calculate capillary action in these two situations, and you will see how it connects to surface tension. Thank you for listening and for staying focused, and we are slowly approaching to the end of this part of the course, so I have to congratulate you on your effort. See you in the next lesson, and good job.